there. Okay, so I want to wrap up this module 2, kind of looking at geology, the basic aspects of geology and seismic data, with a little bit of a seismic analysis summary and showing some case study, and really emphasizing that seismic interpretation is much more than just picking horizons and faults. Okay, so just to kind of summarize, so we took a while ago in some lectures, we understand the rock physics. We understand how it relates to the seismic response. I love this picture because we can see in this outcrop, where we might expect all the peaks and troughs that we're going to be looking at as seismic interpreters. And then we looked at the basics of structure and stratigraphy in seismic. We talked about classical seismic stratigraphy, looking at it in one dimension, so like the 2D vertical section with the on lap and the down lap and top lap. And we talked about all of those techniques in seismic stratigraphy. And then we talked about seismic geomorphology and how we want to understand our analogs. We want to try to find more of the geology in the seismic data than is really apparent. And so I talked about this in the last lecture, really honing in on these small scale like blips and features that we may not initially see in the seismic, but that are there and can be revealed. And so what we're going to get to in the next section is seismic attributes, which I get very excited about. Like those are my thing. What I want to talk about with seismic attributes and introduce as we move forward is that seismic attributes are just math. So they're algorithms that we apply to the seismic data, or maybe we're focusing on just the amplitude. We talked about coherence already, so we wanted to compare one waveform to the one next to it. We can look at like spectral decomposition. We talked about frequency just a little bit, where we're really honing in on certain frequencies or adding them together. And so as we get into seismic attributes, I want to remind you all that it's just math, and it's just allowing us to see different patterns in the data. And so when we talk about seismic attributes, they're these things that are directly sensitive to the geologic feature. Okay, so that kind of like directly, we pick out our attributes based on what we want to see, the purpose of our seismic interpretation. So maybe we pick out attributes that'll help us reveal more information about the structure or the sedimentary features in the seismic. Maybe they're more related to reservoir properties or porosity, migration pathways, all of that information. And so I don't know, I keep saying every time I give this lecture that I want to add up how many seismic attributes there are. But I think that would take me a long time. So, there's definitely more than 50 of them. I'd go into we could probably come up with 100 seismic attributes. Whether they're all useful is up for debate, or that's significantly different from each other. But all of these attributes, they really, really help us understand the geologic structure, the stratigraphy, those rock properties that we're interested in. And so, while I'll focus on seismic attributes next, I will introduce how we have started to use these attributes in terms of as inputs for machine learning. So all sorts of different machine learning, which is also something I spend a lot of time researching and working with students on. And so just to remind you the usefulness of the seismic attributes, here's a time slice looking at amplitude data in a seismic volume in the Gulf of Mexico. And as we look at it as an interpreter, like as an experienced interpreter, I'm paying attention to the differences in amplitudes. I'm noticing there's some interesting lineations in here, that I might start, relating to, they look a little sinuous, so I may relate them more to channels. Some of these straighter ones, I might be like, okay, is that a channel or a fault? But if I spent that, again, few minutes to run a coherence volume in my software package, I would quickly notice that we've got kind of this very complicated channel system. And they show up really quickly. I can then have a lot more confidence in my interpretation. So that's another way to use attributes, is to increase the confidence in your seismic interpretation. And so what we're going to look at as we move through the rest of this course is a lot of seismic attributes, a lot of different depositional systems that we'll go through, because there's so many different patterns that we'll end up seeing based on the depositional depositional systems. And I really believe that the more seismic that you look at, whether it's playing around with it on your workstation or reading about it in journal articles or seeing it in a lecture, the more familiar you are with the seismic expression of these different depositional systems, the better of a seismic interpreter you'll be. So we're going to start going through that and really building up our experience and our abilities to recognize these patterns. And so after that, in a later module, I'm going to get into some more advanced techniques. And so these are things like amplitude anomalies, so our direct hydrocarbon indicators, AVO analyses, and seismic inversion, as well as the 4D time-lapse seismic I've briefly talked about, and then the machine learning. And so these will be what I wrap up the later portions of this lecture series with, now that we've kind of established our fundamentals. And so I want to show a quick case study that was done by one of my students. This was a master's project, but she stayed on and did really great work as a PhD. But I like showing this as an example of where we can go with our seismic interpretation. So in this case, we're looking at a deep water channel system. Corellia was originally a student of Roger Slatz, who was a well-renowned deep water reservoir researcher and educator. And she had gotten interested in seismic attributes and how we can get more from seismic data and even machine learning. And so just to kind of quickly go through what was a year worth of work in like 5 slides, what the area we're working in here is in the Taranaki Basin. So I've shown a lot of examples there. It's a nice area. It has more modern seismic data that's available for researchers to look at. A lot of wells in the area, and so it's very well studied. There's production that's gone on throughout the Taranaki Basin, hydrocarbon production. And we're going to be looking at a deep water Miocene area. And so, of course, in the first stage, like I've been trying to teach you, same way I teach her, we want to think about the deep water systems and what different features are we going to anticipate. So in this case, her seismic volume, it comes off of the shelf into the deep water, out into the slope of the system a little bit. So we want to think about the different buildups of levee systems, of larger scale channel complexes. Maybe there's going to be the presence of those overbank sediment waves. So we're trying to like root ourselves in what is known about this area to start off with. And then, like I've shown you, one of the things I like to have my students do is try to start to put together a summary of what they know. Okay, so with her data, and of course this was done after some work was done, but it's a good way to start sketching it out and build upon it. So there's certain architectural elements of the channel system that she'll start off expecting. In this case, she put in kind of like the geologic scheme, so the cartoon of the system to kind of remind her what there may be. Describing the internal seismic reflection configuration, so what we might see, the external shape, what the amplitude may look like in terms of how low or high it may be, and then an example of what it would look like in a vertical slice or in a time slice. So if we pick one of these, here we're going to do mass transport deposits. Okay, so we've got mass transport deposits. We know roughly what they look like. We've got these slope failures and slumping features. They can be subparallel and they can all the way to chaotic. So they have a little bit of variation that we would expect. They could look like rotated blocks. They could look shingled in terms of their external shape. And in terms of amplitude, it's going to be very variable. So depending on the lithologies, you could have higher or lower amplitudes. Generally, they tend to be more mud-rich and so often lower amplitude. And so here's an example of what one looks like in a vertical slice and in the time slice. Don't really see much in the time slice, but it's good to put in there. All right, so in this case, we've got over here a time slice through our channel system. Okay, so I want you to, and we've got our time slice and we've got our vertical section here. Okay, and so if we look at our time slice, okay, I've seen this like a million times. You know, like I could kind of see maybe like a kind of sinuous feature in here, something I wouldn't have a lot of confidence in just looking at the seismic amplitude. In vertical section, I can clearly see what Corellia sees. I can see some channel belts. I can see some levies, these kind of harps, so high amplitude reflectors, may be related to fans or sheet sands, which we would also expect in the system. But of course, so that's kind of like where we are right now at the stage in this course. But where we're going to build to is starting to use seismic attributes to get more information out of the seismic data. And so at the end of her study, she had selected several seismic attributes, and I'll talk to you about all of these in details. And again, went through the same thought process. What will these look like in a coherence sense? All these different features, or curvature. We've got texture attributes, frequency attributes, reflector convergence attributes. So thinking about all of these and how they'll relate to each channel architecture in that system. And so, of course, what we're going to do first before we get into machine learning is we're going to examine each attribute individually. Okay, and so I'm just going through this really fast, and I'll slow down when I talk about these later on in next lectures. But so in this case, we're looking at 4 different seismic attributes. We've got here our GLCM entropy. So it's kind of a texture. It's giving an idea of like the pattern of the data. So kind of compare it to rubbing your thumb against sandpaper or a soft sweater. So those are different textures that we're trying to detect in the seismic. How much do they vary? We've got our RMS amplitude. So we're looking at an amplitude. How high are those amplitudes? We've got our coherence here. So Sobel filter is a type of coherence type attribute that we use often. And then we've got a spectral. So we're looking at texture, we're looking at amplitude, frequency, and then like our edge detectors. And so from all of those, you can start to notice, without me talking about them too much, and like with your geologic goggles on, that we can kind of see different aspects of a channel. So we've got this minor channel marked in pink down here in coherence, which is pretty easy to see. It pops out to us. We've got our larger scale channel complex. That really starts to appear on a couple of these attributes when we look at them together. We've even got some sediment waves, which look really lovely in the amplitude data. And so where we can go from there, just as one example, is we can use unsupervised machine learning to cluster parts of the seismic data that look similar to each other. And so this is a case of 3 different self-organizing maps. So one of the methods we can use, there's many of them, using different combinations of attributes. And so in this case, we've got 4 attributes being used in SOM 1 on the left, 5 in SOM 2 and SOM 3. And in all of them, we can pick out different aspects of the architecture. So there's not always this one perfect machine learning solution that solves it all for us. And when we look at them side by side, there's some aspects we could see, like the sediment waves look a lot better in SOM 3. They're not as apparent to me in SOM 2, even though you could still pick them out. Some of the internal channel architecture doesn't look quite as great or quite as apparent, let's say, in SOM 1 as it does in SOM 3. Also, we could look at them in time slices. We can look at them in vertical section. And of course, we can compare them to the original seismic amplitude data. So you could see how going from seismic amplitude data, which is pretty much what we've talked about in these last 2 modules of the course, to seismic attributes, and then machine learning can help reveal a lot more of these patterns that we want to use as seismic interpreters. And so this is where we're going to go in the course. And so as we finish up, I just want you to kind of always remember the basics when interpreting. So it all goes back to impedance differences, which we can relate to the rock properties. Depending when you're choosing workflows and figuring out what you're trying to do, whether it's seismic geomorphology and different illumination or slicing patterns, you want to know why you're interpreting, because you can see with the variety of techniques I've already touched on, and there's many more I'm going to touch on, you could spend forever interpreting one data set. And so always kind of keeping in mind and keeping yourself grounded as to why you're doing what you're doing is really useful, so you don't get lost. You also want to know the limitations of your data, whether it's from the frequencies that you have available to issues with acquisition or processing. And then remembering that this is all about pattern recognition and taking the seismic data, which is essentially just a grid of numbers, a giant grid of numbers in 3 dimensions, how we can turn them into waves, use different colors, different aspects of the seismic data to help us see the patterns that then we, as humans, interpreters, we can use our geologic analogs to really reveal what's happening in the subsurface for whatever purpose we're looking at seismic data for. So with that, hopefully you can see where we're about to go and kind of remind yourself of the key aspects of what's been important and what we've talked about already. So thanks so much for listening.